Thank you, Yuri. So my goal for today is to tell you a little bit about the kind of thing we've been doing for the last decade. Something we believe might be the future of cryptography. I'll try to convince you of that. So it's something called lattice-based cryptography. And let's try to make this interactive. Otherwise, you can just watch the YouTube recording of this talk. So I'll ask you questions, and you'll have to ask me questions. Um, so I'll start very slowly. We're after lunch, so I won't rush it. If there's something, I'm not used to giving such a broad audience talk. So if there's something that's not clear, let me know. I'll try to go slowly. So let's go back in history. Cryptography dates back millennia and hasn't changed much over most of history. So this is like 16th century, and the idea is, as you might expect from naive cryptography, like you flip some letters, change something, you want to send a secret message, that's how you would do that. And this is Second World War, the Enigma. But still, in some sense, it hasn't changed much. It's much more sophisticated, but still mathematically, it's based on similar ideas of like garbling things, so you don't really know what's in there. But cryptography as kind of a mathematical field and a theoretical field only developed much more recently. I would say around the 70s, the 80s, we started getting a good theoretical understanding of what cryptography is all about. So perhaps one of the biggest conceptual breakthroughs came in the 70s, where people realized one can do public key cryptography. So public key cryptography is something we all take for granted. So now when I take my phone now and I log into my bank or to Gmail, the communication is encrypted, even though I never set a secret in advance with my bank. So historically, when some spy goes over, has to take his machine with him or some secret book with him, that was the way things were done historically, with secret encryption, secret key encryption. Nowadays, things are done using public key encryption, which doesn't require me to set any secrets in advance. So I'll mention this in the next slide. It was discovered publicly by Diffie and Hellman in 1976, and more recently it turned out that the British intelligence, the GCHQ, knew this 3 years earlier, so Cox especially. And I think this is conceptually, like if I ask people in the street if they've ever heard of a black hole, they would probably all tell me yes. But I don't think enough people know about the fact that one can do something so conceptually amazing. And the idea is that there are two parties, they want to communicate secretly, and there's someone listening. Okay, so I could now talk to Dan. You can all hear everything we say, and I can transmit to Dan a secret message, and you wouldn't know what's in there. If you think about it, it's amazing that something like that can exist, because you all hear the same thing Dan and I hear. It's all publicly. So this is the idea of Diffie and Hellman. Perhaps if you've never seen this before, I should say the reason why this is possible is because the eavesdropper can hear everything but can't look inside your brain. So you know something that the eavesdropper doesn't know, and you'll see in a minute. Actually, how many of you have seen an example of a public key encryption system? A show of hands. How it works. Okay, you've all seen it. Okay, so you'll see a new one today, one I haven't seen before, I think. And the one you've seen, I imagine, is the RSA system. So this is the one most people know of. That's the one we teach in our graduate courses. It was developed by Rivez, Shamir, and Edelman in '77. That's the one used almost everywhere nowadays. You log into your bank, and everything is based on their protocol. So and it stood, it still stands for many, many years. And the RSA crypto system is again, as I said, it's everywhere. It's in the credit cards and phones, and it's based on a certain problem, certain mathematical problem, namely the factoring problem. So we all know what factoring integer means. I give you 15, and you have to tell me it's 3 times 5. 21 is 3 times 7. 55 is 5 times 11. But 1843 is, it's not such a big number. Come on, you can do that. Okay. Yeah, I'm disappointed. I thought it's such an audience I should be able to get an answer. Okay, 97 times 19. Yeah, not so bad. But you see, you get a sense that this is a hard problem, and indeed this is what RSA is based on. And this is not like squaring a number or square root. There's no simple recipe on how to factor an integer. And that's exactly what RSA is based on. So if you take even a bigger number, something like that, it's a long number, but it's not like unreasonably long. Like if I want to compute square roots, I could easily do that. A computer can in no time take square root or square this number. It has 200 digits only, right? We deal with much bigger numbers, but factoring this number, it is known that this is a product of two primes, but finding those is the challenge of $30,000 by the RSA company. It used to be challenge. It is a product with primes, yeah. And I think this one's actually around 2007 was actually broken. So I should say that the latest record is factoring a number with 232 decimal digits. And that took 2,000 computer years, which is not as much as it sounds because you just use 2,000 computers and run each one for a year. But it's still, it's of effort. So for government organizations, this is not unreasonable. Naive, if you think of naive algorithm, you would just try divide by 2, divide by 3, divide by 5, and so on up to dividing it by the number itself. That would take you more than the lifetime of the universe. If you're a bit smarter, you can stop at square root a number because one of the factors has to be that big, but doesn't make it much faster. Well, significantly faster, but still extremely, extremely slow. But turns out there's a highly non-trivial algorithm, this number field sieve, and that runs in time e to the n to the 1/3. So n is number of digits. And that's partly the reason why nowadays when you use RSA, you tend to use very big numbers like 1,000 binary digits or 2,000 binary digits. It's because there are highly non-trivial attacks like this that allow you to factor numbers. But this is the fastest we know already for 2 decades. It's a beautiful algorithm, but that's the fastest we know for 2 decades. And that's based on this algorithm, we set the parameters we use in RSA. We say, okay, 2,000 bits should be safe. I should say, for those of you who have heard of NP hardness, I should say this is not this problem, and similarly, all problems in crypto that we base crypto on are not NP hard. Okay, it's not believed to be NP hard, but there's a reason for that. So those are problems that we don't have very strong confidence in their hardness. So it's kind of more empirical evidence. Question?
You said it's not believed to be NP hard. It's not really.
Well, there's a technicality here that maybe P equals NP. We don't know anything in computation and complexity, but yeah, but there's a very strong evidence that I would say, yeah, it's known not to be NP hard, you know. Thanks. So, and as I said, this is kind of the basis of all secure communication. Basically, most of economy is based on, we need to communicate with each other. We need this assumption that factoring integers is a hard task. There are similar tasks of the same flavor. This is not the only one. There are discrete log and other things of that kind, but they all roughly have the same flavor. So basically, all of Earth is standing on this one pillar. But as you might have heard, things are not that bright for factoring. And this is something that happened in '94 or in the mid-'90s. Basically, this pillar turned out to be not as stable as we thought it is. So we don't yet have a kind of normal algorithm to factor numbers. It might exist. Some mathematicians say that, yeah, there should be an algorithm for factoring integer, efficient one. We don't know yet if it exists or not. But turned out in the mid-'90s that, and this is Peter Shaw over there, he discovered that factoring is easy for a quantum computer. So this is this pillar we had before. It turns out there's an earthquake and the pillar is broken. So quantum computers can break almost all cryptographic codes in use today. That's basically what Peter Shaw told us. Why am I still using my phone? Why am I communicating securely here with my bank? Well, turns out that quantum computers don't exist yet. And maybe in the mid-'90s, people didn't know, will quantum computers ever exist? I'm still not sure. I'm not a physicist. I don't know. But there's more and more evidence that maybe quantum computers will exist. Just, I guess, a few days ago, 2-3 days ago, there was a story. There was an article published showing, possible avenue for creating quantum computer. And I believe Andrew Mills was one of the authors in this research, and showing that the expectation that in 10 years we will have true quantum computer. So there's more and more evidence. Many groups are working on this currently, and there's more and more evidence that we will have very soon quantum computers. It's like fusion. I've been hearing this for a long time, but now they're really serious, right? You promise? No, you don't promise, or you do?
No.
Okay, this is the reporter's fault, right?
This is entirely the report.
Yeah, you can see Microsoft maybe. Yeah. Okay.
All we said was if you had a small quantum computer, you could do this following
Okay.
thing with it. We didn't say how to build one.
Okay. Yeah, it's just a great headline. Yeah. Yeah. I have some more examples of that. Yeah. But I was okay. I mean, I think it's fair to say there's lots of progress in recent years. It doesn't seem like something totally outrageous, and I'm not the only one saying it. That's led to the development of this area, what might call post-quantum cryptography, like what cryptography should be used once quantum computers are built, and something people really worry about now, because the communication we use now should be secure also in 5 or 10 years, right? Because the enemy might eavesdrop, might save the entire communication You don't want the national secrets to be revealed in 10 years. And just in 2 months ago, the NSA announced its plans to shift the encryption of government data away from current cryptographic schemes, namely based on factoring, to something new. They didn't say what new is, but I have an answer for you. I have a good suggestion for them. And I think this is maybe currently the most viable, most mature alternative to RSA and other factoring-based schemes. So this is what's called lattice-based cryptography. So before I get there, I want to show you a simple, very simple public key encryption, because not all of you know how public key encryption works. And this is something you can show to your cousins, your kids, your grandkids. This is something that high school kids can easily do, and you can do it even in experimenting in classroom. So let me try to do it with you. A really simple public key crypto system. Okay, so I'm trying to, again, sorry, Dan, again, I'm picking on you. So you're trying to send me a message, trying to send me yes or no, just a 0, 1. And the way I would do that is this. I would pick a random number. That's going to be in my brain. I'm not going to be in my head. I'm not going to tell anyone. So I pick a random odd integer, 1001, okay, but I'm not telling you. You don't know that. And I'm going to send over to Dan, and you can all hear that, random multiples of this number. So I'm just multiplying them, let's say, multiply by 98, and I'm going to add to that a small even random number. So I multiplied by 98, it's going to become 98,098. I'm adding 2, so I get 98,100, 98,100. And I'm going to do it a couple of times, like 100 times. And I'm going to send all these numbers over to Dan. Okay, you can all hear that. That's fine. What Dan next does is he takes a random subset of those numbers and adds them up. So he takes, picks half of them, say, roughly, randomly, and adds them all up. If he wants to send me the message 0, he just sends it as is. But if he wants to send me the message 1, he also adds 1 at the end. Okay. So again, I have this list of numbers. Dan adds a random subset of them and sends it over. If he wants to encrypt 0, if he wants to encrypt 1, he also adds 1 at the end. That's all. How do I now decrypt? So you're not supposed to be able to tell anything based on this, because you just basically see a bunch of those numbers with some error in them. I'll tell you later what I know to say about this, but it's believed that you won't be able to do anything. But how come I can do something? Because I know something that you don't know. I know the number S. I know where all these numbers, the 98,000 and so on, all came from. I know 1,001. What I can do now is I just divide this number by 1,001, and I get the remainder of 9, and then I know that because this remainder is odd, I know that Dan meant to send me 1, meant to send me the message 1, not the message 0. And the reason it works is because you think about all those numbers. If you divide it by 1,001, you'll get an even number as a remainder, right? That's how I chose them. I always added an even random number. Hence, if Dan sends me 0, the remainder here would also be even. Sum of even numbers is also even. But Dan sends me 1, hence the remainder here is odd. Does it make sense? Okay. So this is basically the idea. This is how I decrypt. I compute the remainder under division by the secret S, and if it's odd or even, based on that, I know the answer. Right, so I should choose this number big enough. This is, of course, just an example. The numbers are very small, right? So this number should be big enough not to have an overflow, right? And actually, this was presented in one of the popular science magazines, and there was a comment there by one of the readers saying, here's a spreadsheet I did, and it doesn't work. I don't know what's wrong with it. Can someone please help me? Basically, just choose a very small number, 7, nothing worry. But then I told him, yeah, this is what you should do. Choose a big enough number. But this scheme is not just, I'm not just showing it for fun. Amazingly enough, this scheme embodies the main ideas that we have in lattice-based cryptography. So this is, in a sense, if you modify it a bit, is a lattice-based crypto system. The initial ideas, as I'll mention later, date back to work of Aitai and Work in 1997, and something I did in 2003. But amazingly, because it's so natural, this was discovered independently by several researchers. For instance, Bram Cohen is the inventor of BitTorrent, also suggested at some point use something like that. But the main thing I'm trying to convey today is not just this, of course, but that there's a good theoretical reason why we believe this is hard. It's not just a game. And this is something I should maybe emphasize. In cryptography, it's very tempting just invent things that seem like they should be hard and secure. And there's this tension between two communities in the cryptography where some people just say, oh, here's a great idea. This should be secure. Just multiply numbers, square them, and often it does, but sometimes it's not. So if you really want to be secure, you want some more evidence. If you want to use something for decades, you want some more evidence. So for instance, in the case of RSA, you might say, okay, the evidence is because factoring is a hard problem, and it has been for decades, has been investigated. Even though I should say, just as a comment, it's not actually provable that RSA is based on factoring. There's a little known secret there, but that's a minor issue. Okay. This is not RSA at all, actually. This is something that I'll talk about. This is the topic of today's talk. So this is lattice-based cryptography. It's not related to RSA as far as I know. It's something completely new. This is what I'm promoting as the replacement for RSA. So I'll give you more details about this and where this comes from. RSA is different. I would say you can't explain RSA to maybe high school students. You need for RSA, you need exponentiation modulo some prime or something. Not much more modulo composite, but it's not much more complicated. This really, I think it's much simpler because you only have to add numbers. You don't have to exponentiate. Yeah. Good. So that's a good question, and this is one of the reasons why I'm here. Yeah, we believe that this is safe against quantum computers. I should say, I mean, if you know a bit about Shor's algorithm, one of the things it uses is this periodicity, that the quantum computers can perform a quantum Fourier transform and recover a period of some function. And you might be worried that also here I'm using I'm using a period, I'm using multiples of a certain number. And initially, there was the fear that maybe this is also something that's susceptible to the same kind of algorithms. But I think nowadays we understand that this addition of noise is really crucial. This addition of noise is what distinguishes these things from what you typically see in RSA or other systems. Noise really changes the whole picture and seems to make quantum algorithms fail. But exactly, yeah. So when I say noise, I just mean those random perturbations, those random numbers you add. Yeah, yeah. Because okay. It's hard to say, right? I mean, we don't know anything. Maybe factoring has an efficient algorithm. Maybe this has an efficient algorithm, but it's only empirical based on lots of attempts. And I'll say more why we think this is hard. There's a reason why we think this is hard, but again, there's never a proof in this area. No one has a proof that factoring is hard. No one has a proof this is hard. Okay, it's only evidence, strong evidence in this case, I believe. So before we get there, so what is a lattice? Well, when I pronounce it, it's kind of the same. So it's a lattice and a lattice. But you see the lattices are kind of arranged on the lattice here. Yeah, one day I should ask someone to explain to me. But so this is a two-dimensional structure. And so we heard in Sharon's talk, we talked about three-dimensional lattices, also tan lattices. And in Sergio, we were in 4 dimensions. Here it's going to be more. It's going to be like 500 dimensions or something growing to infinity. We usually think in this area, we think of high-dimensional lattices. So this is again, two-dimensional lattice. This is some kind of 3D rendering of it. Mathematically, lattice is simply a set of points with some periodicity to them, or if you like, you take n vectors, v1 up to vn, and take all their integer combinations. Okay, so that's v1, v2, and this is like 2v1, 2v2, v1 plus v2, and so on. So you have all this integer combination. So it's a bit like linear span, except you insist on the coefficient being integer, and that gives you this discrete structure. So if you wish, it's a discrete subgroup of Rn, and those are a basis. Those are basis of N. Okay, so this is something we call a basis. So it has an interesting, regular pattern. It's in Rn in high-dimensional space. That's crucial for our applications. So that's a lattice, and v1, v2 is a basis. So in the history, we've heard a bit about this from Sharon. Those date back to the early days of mathematics. They've been investigated a lot in the 19th century and before. What they cared about, Lagrange, Gauss, Hermite, Minkowski, and many others, this came from number theory. They mainly cared about number theoretic equations. So for instance, there's a famous theorem that says that any number can be written as sum of 4 squares. You can prove it using those ideas, using lattices. So 310 is the sum of those 4 squares. I don't know why all these people are so grumpy. It's actually a nice area to work in. There's lots of connections to other areas. It's not nothing wrong with that area. So one thing that makes this interesting for us in computer science is that the basis, this thing that generates the lattice, is not unique. Or you know that from linear algebra, but here it gets a special meaning. So v1, v2, you might think generate some kind of elongated lattice or something in the direction of V1, V2, but turns out they actually generate a perfectly reasonable lattice, and that lattice has a different basis, this V1 prime, V2 prime. So there's some freedom in choosing the basis, and what makes it so interesting for us, remember factoring, to make public encryption work, we need some hard problem. And the hard problem for us, the factoring for us, is something called the shortest vector problem. And here the problem is this: I give you a lattice. What does it mean? I don't give you all the vectors because there are infinitely many of them. I only give you a basis. I give you n vectors, v1, v2 up to vn. Those are typically long vectors. They'll have very small angles between them. And your goal is to find the shortest lattice basis, okay? The shortest vector in the lattice they generate, okay? Not zero. Zero, I know it's there. I want something that's non-zero. So I want a non-zero shortest vector in this lattice. Okay? That's the task. And again, as you saw before, it's hard from v1, v2 alone. It's hard to see how to get those short vectors because of those cancellations. So you can, in this case, you can take 3 times v2 and subtract 4 times v1. That might give you the shortest vector. Okay. So it really depends on the intricate geometry of v1, v2. And this, we believe, is a hard problem. So the best known algorithm, and this has been investigated also for decades, since the early 80s, the best known algorithm runs in time 2 to the n. So n being the dimension here. So as you can see, it's extremely small. And around, we can maybe handle up to dimension 100, but above that, we really don't have a good way of finding shortest vectors in lattices. And answering your question, we don't have any better quantum algorithm here. Nothing that does anything better than 2 to the n. Okay. Often you get some small advantages coming from quantum computer, like square root advantages. Even that doesn't seem to exist here, as far as I know. Yeah, the matrix would be n by n. So there are n vectors in n dimensions. Yes, yes. So the input would have n squared scalars. And, yeah. So basically, trying to find those combinations that lead to short vectors. One thing that is known, I should mention as a digression, is a very famous algorithm. It's known it's one of the nicest algorithms that exist. The LLL algorithm, Lenstra, and Lovász. You can see them there, around 82. And this is one of the classical results in this area. It's a bit of a digression because it's not relevant directly for what I'll talk about next, but it does something incredible. It does manage to output a somewhat short vector. It's not the shortest, it's not even somewhat short. It's only 2 to the n or 2 to the order n times the shortest. So if n is big, this is quite bad, but often in applications, n is rather small. In applications that, not cryptographic applications, other kind of applications. And there, this might be useful, very useful. And indeed, this algorithm found lots of applications. So you can solve integer programs in a fixed dimension, factor polynomials over rationals. One very nice application I think more people should know about is something known as finding integer relations. Basically, if imagine you run some experiment and you get some number out of it, some numerical estimate, 5.709975, and you kind of wonder, maybe this number means something. Maybe it's some algebraic number. Maybe it's So does anyone know this number? Because this is a basic number. It's an important number. What? So yeah, it turns out this is 4 plus cube root of 5. Okay. And you could actually find it. You could go to this website and called the inverse symbolic calculator, and I just used it a month ago from some result in some semi-definite programming I was running, and suddenly it gave me e to the power 4/9 or something times pi. So it was, it taught me something I didn't know before, and this website does something much more than just LLL, but that's where the ideas come from. So if you have a number, some experiment, you want to see if the number means something, you can go there. So this algorithm was also used a lot for attacking cryptography, something known as knapsack crypto system. Even RSA was attacked in some cases using this algorithm. Beautiful work, Hastad Coppersmith. But what I'm going to talk about today is another kind of application of lattices, namely to build new cryptographic schemes. So this came with fantastic work of Aitai in the mid-90s. And he was the first to realize that the fact that we have those lattices and there are some hard questions related to them, that should allow us to build cryptography, to construct new kinds of cryptography, not RSA, nothing based on factoring. This was his realization in the mid-90s. Basically, he gave a way to do public key encryption using those lattices, assuming this hardness of finding short vectors in lattices. I'll say more about this in a minute. But at that time, it seemed just like a theoretical curiosity. It seemed not so useful, very inefficient. In recent years, the full power of lattice-based cryptography is finally understood. So I would say in the last 5 years, we finally see what this is so good for. So I'll try to give you my sales pitch. So this is why should you use lattice-based crypto? So I hope the NSA are listening or whatever. So recent work tells us that there are lots of advantages of this lattice-based crypto compared with traditional RSA crypto. Let me start with the kind of security proofs we have. So we have provable, what I call provable security, which means the following. It's a mathematical statement which says that if you break lattice-based cryptography, if you can find, like during this communication with Dan, you manage to find the secret, manage to find Dan's secret, then just because you have a way of attacking this communication, that implies that for any given lattice, you can find a short vector. So if you think about it, it's a very strong statement. It's something you don't usually see. Even in RSA, you never see such statements that tell you if you break the crypto system, even with some small probability, that immediately implies a way to find short vectors in any lattice, something we consider highly unlikely. Okay, so so I want to emphasize the importance of this. Again, it's tempting to suggest, if you want to build new cryptography, it's always tempting to suggest some, great, brilliant ideas, some, maybe, multiply by 2, divide by 5. But if you don't have something to back this, the smartest guy down the block might have might find a way to attack this. And this often happens in cryptography, unfortunately. I mean, for better or worse, it has some advantages, but you often see this cat and mouse game where someone publishes a paper, the next day someone breaks it, then he patches it, and then the next day someone else breaks it, and so on. So it kind of makes me feel safer, feel more secure if I know that there's some proof behind it. It tells me, yeah, if you break my crypto system, I know something major will happen. So this is the first point in favor of those systems. This doesn't quite exist in RSA-like systems. If you break RSA, you might be able to factor certain kinds of numbers. So maybe some composers are easier than others. Yes, definitely. So even if you do it like with probability 1% or 1 in a million, you can still do that. Definitely, yeah. This is necessary. All of cryptography has to be probabilistic. The second point I was alluding to before is that we believe it is also resistant to quantum computers. So far, there's no quantum algorithm that can do better on these questions, whereas all number theoretic crypto is already broken by quantum computers. The third point I'd like to make is that, well, in some cases it's faster, basically because you only have to add numbers. This is not a big serious issue. But this is something very interesting. The last point is something we only realized in the last 5 years. Like when I started working on this about 10 years ago, I would never imagine that this can happen. This was a big surprise to me. Turns out that those lattices are not only secure, but also turn out to be much more versatile and have many more applications. So there are some amazing counterintuitive things one can do in cryptography. For instance, fully homomorphic encryption, I'll get back to later, that one can do using lattices, using those kind of problems, and only using them. And I should say, here's a list. It's only a very partial list of things people manage to do with this. When you hear about cryptography, you usually think of encryption, of sending a secret over to someone else. But that's encryption. Cryptography is actually much more than that. So one task you can imagine is that you call someone over the phone and you want to together jointly toss a coin. Okay, so how do you do that? Well, I can toss a coin and tell you, oh, it's heads. But then the other guy says, are you sure it's heads? So then he tosses the coin and says, no, it's tails. But how do you coordinate this? How do you trust this and priority issue? And turns out you can solve it using cryptography. One example of an application maybe you haven't seen before. It's not encryption. There's no secret there, but it's something else that you want to agree on something. And there are lots of other counterintuitive examples, like identity-based encryption. We have the world's expert here. This allows you to send a message to someone, encrypting just based on the email without any public key from that person being sent to you. Lots of more applications, and this is something I'll get back to fully homomorphic encryption. Just that you know that those lattice encryption systems, those lattices not only allow you to encrypt, but turns out to allow you to do many, many more things. And I'll show you another example later. So how would lattices even be useful for cryptography? What's the connection? So I'll show you just something that you can, some visual picture you can have in mind, even though that's not the way we do it these days. I'll mention later how we do it these days. But at least the early days, that's how it started in the mid 90s. So here is a lattice, and here I choose the lattice. I'm as the recipient. I choose the lattice, and here's the basis I chose. It's a very nice basis, almost orthogonal vectors. But I don't tell you that basis. I don't send you the basis. I only send you a very bad basis. I on purpose ruin the basis, choose a different basis made of very long vectors. This essentially breaks your ability to see the microstructure there. You no longer see the lattice structure. That's the idea by sending you those long vectors. And that's why I should say that's why lattice problems are so hard in high dimension. It's very hard to know where you are. You might be very close to the lattice, but you won't even know that because we're in such high dimensions. It's hard to see the microstructure. So this is what I send to everyone. It's my public key. And then if someone wants to send me a message, they can take a point. Maybe imagine this point represents some kind of message, yes or no. And then all they have to do is perturb it a bit. Just shift it a little bit away from that lattice point. The idea is this. The idea is that now all the eavesdroppers can't tell that this point came from here. Okay, even though it's very close, they can't tell because this requires understanding the geometry of the lattice, which is something that we don't know how to do. Okay, so this is believed to be good encryption because this guy it's impossible. It seems impossible to recover this guy from the guy here, and I, as the recipient, well, I chose the basis. I know the structure of the lattice, and all I have to do now, this is very easy. Once I have this basis, I can represent this point in this coordinate system and then round to the nearest integer. That's going to give me this. Okay, it's easy to see. So that's not really how we do things. It's just for intuition. Yeah, go ahead.
About getting that shortest vector, could it, say you have given the very bad basis, could that person not just generate the Fourier transform with that basis, like a structure factor, and then they will see this point?
Yeah, so you can take.
This basis in it.
Well, if you take, the thing is that you don't really have the function instead of this picture in front. You only have the basis. That's the problem.
Just from the basis.
What you can do, you can generate the basis of the Fourier transform. The Fourier transform is also a lattice. And you can generate, by taking the dual of that, or the inverse of that matrix, you can generate the basis of the dual. But you're still stuck with the same problem that you have a basis of very long vectors, and you don't see the short points. You won't see the short points in dual either. Yeah, but duality is something we use a lot, and I'll get back to it later. Yeah, Fourier transform is something we use all the time. It's a good point. So the way most of this work happens today, most of lattice-based crypto is based on the problem that called learning with errors. Maybe somewhat of a bad choice of name at the time. We didn't know what it would be used for. So this was this is the following problem. So it's a very basic problem. And it's used, I'll tell you in a minute what it is, but it's used as a kind of intermediate between cryptographic applications and lattices. So basically it tells you, you can, if you wish, you can just forget about lattices and only worry about this LWE problem. And this connection is something that we can prove that this LWE is as hard as lattices. And if you want to construct something like public key encryption or fully homomorphic encryption, you only have to worry about this LWE problem and use it as your building block. And that's what all those papers I mentioned before, that's what they do. So it's actually a very simple problem. The basic idea, the basic question there is how to recover hidden periodicity. Okay, so here's an example. So imagine you have this probability distribution, some kind of periodic Gaussian, and what you're seeing is not this whole plot. You're only seeing samples from the distribution. Okay, so the distribution is parameterized by the number of peaks. Okay, in this case, I think 1, 2, 3, 4, 7. And what you're seeing are samples from the distribution. So basically, you're seeing numbers that are close to multiples of 1 over 7, 1/7. Okay. So here's an example. So I took say n equals 1,000. This is my domain, and here are a bunch of numbers. And I tell you, all those numbers are very close to n over something, n over some k. And your goal is to find out what that k is. What's the hidden periodicity here? Notice again the appearance of noise, right? It's not that I'm really giving you multiples of that 1 over 7. I'm only giving you this with some perturbation. And that's what makes it so hard. You can no longer use things like GCD, or if you know Shor's algorithm, that's what people use there. It seems to make it much harder. Just this addition of noise makes the problem much harder. So in this case, does anyone see this? This is all very close to multiples of 1,000 over k for some k I don't tell you. So this all turned out to be close to 1,000 over 13. But you can see, you can get a sense that this is hard to deduce from this list, and indeed this is what we're using. That using those this hidden periodicity is a hard problem. Okay. So more precisely, I'll change it a bit just to make it more convenient for later. The problem is this: there's a secret number S, so it's a number modulo some big number capital N, and your input is an arbitrary long sequence of pairs AI, BI, chosen such that AI times S is roughly BI. Because I'm making it inhomogeneous. I'm adding those BIs on the right-hand side. But these are all just, this is all very basic math, right? I'm just talking about multiplication, modulo n, and this approximate equal means up to some Gaussian noise that I'm adding to each equation. Okay. So this is basically the problem. The AIs are uniformly distributed, okay? And the BI is of the form AI times S plus EI. EI is some normal, some Gaussian noise, some normal noise added to each equation. So in this example here, okay, you have this list of equations. You can have many, many of them. Can you find S? Okay. So this is, as you can see, this is a very basic problem. If those were equalities, well, then I know how to solve it. I have one such equality. I can easily invert 251 and recover S. But those are not equalities. And this is totally crucial here. There's some noise in each equation. They're not exact. Okay, so the goal is, again, to find S, or just distinguishing this from uniform, just saying that those equations have some S in them. This already is believed to be hard. So what's the connections? Now I gave you this problem, this LWE problem. What's the connection to lattices, right? It seems like something totally unrelated. The question seems hard, but can we give any strong evidence for why it's hard? Okay, so it's, the running time, the best known algorithm is something like N, basically try all secret S. We don't know anything much more clever than that. And it turns out, and this is a surprising fact, turns out this problem is closely related to lattice problems. Okay, even though it's just a problem about numbers modulo N, there's nothing fancy going on here. No lattices, nothing. But turns out, and you can prove this, that LWE with this modulus N is as hard as worst case n-dimensional lattice problems. So let me say it again. So if you can solve that problem I told you before, given this noisy equations, if you can recover S, even with some small probability, even if you use tons of equations, that automatically implies that you have an efficient algorithm for solving those n-dimensional, those shortest vector problem in lattices. Okay, finding short vectors in lattices, which is something we believe is very difficult, highly unlikely to be possible. Does it make sense? So this is what security proofs look like. You assume there's an attack on your crypto system. You show something, unreasonable happens, and that something unreasonable here is solving the shortest vector, short vector problem in lattices. Make sense? So actually, I'm cheating you. This is my dream theorem. This is not actually what we managed to prove. What I proved is actually slightly weaker than that, and this is how it's weaker. And this is a fascinating thing for me. For years I was trying to improve it, but don't know how to do that. So hope to get some help. The theorem is only using what I call a quantum reduction. So what does that mean? It's something that I haven't seen anywhere else. So I'm really hoping to understand better what's going on here. But the theorem, what I wanted to have is that solving this learning with error, solving those noisy equations, would imply that you have an efficient algorithm for a shortest vector problem. Unfortunately, the only thing we can show is that you get an efficient quantum algorithm for shortest vector problem. Okay, so this is the quantum there. It's a bad thing. In this case, quantum would be a disadvantage. I wish we didn't have it there. Again, it weakens the conclusion. It says that the system is secure, assuming now that quantum computers cannot break lattices. Yeah.
If I gave you a quantum algorithm for LWE, could you propose that with
Yes.
quantum reduction?
Yes. So actually, this is how it came about. I was hoping to solve lattices and then saying, okay, let's just solve this problem first. Surely it's easy, right? This sounds a lot like the problem in Shor's algorithm. But there I got stuck. So I said, okay, let's give it a different spin and let's write a paper about cryptography. But yeah, this was the initial idea. So again, this weakens the statement. Nowadays, there are some, we know how to partly get rid of this. So I should say there are some nice results by Pikett and others trying to get rid of that quantum part, but it's not fully understood yet. But luckily, this is still consistent with our belief that quantum algorithms are cannot break lattices. Okay, so this is still considered valid, security statement of that form, and in some sense, anyway, the minute we have quantum computers, if quantum computers can break lattices, everything here is anyway gone. So this assumption is necessary in some sense, but I'm sorry if it doesn't make sense. So this is the main theorem. Again, it gives us some confidence in this LWE problem and tells you that now if you want to construct, your favorite cryptographic system, you just have to use this LWE problem and do whatever you want with it. So let me tell you a few words about kind of what goes into the proof. I'm not going to do the proof here, just so you see some of the ideas. And one of the ideas comes to deal with the following issue in this statement. If you just kind of stare at this mathematical statement, you see that on one hand you have this cryptographic problem, LWE. It has almost no parameters. It's basically choose a random number and just generate those equations. There's no input really to the problem. I mean, there's this number, the modulus n, but that's not the input. That's just just some discretization. And on the other hand, we have those n-dimensional lattice problems. So we're given a certain specific lattice. We have to solve that specific lattice, find shortest vectors in that specific lattice. How do you do that? How do you make this conversion to something that does not depend on your specific input? And the idea is that of blurring. So Gaussian blur, you can do it for images, and you can also do it for lattices. So you can take a lattice and add more and more blur, and it turns out that very quickly you get some uniform continuum of something that's essentially flat, and you can prove mathematically it's not very difficult, that this is indeed what will happen if you take a lattice and add Gaussian noise, a bit more, it looks like an egg carton, and then you add a bit more, and you very quickly get something that's extremely flat. This will just just double the radius each time, and this is what I get next. So this is not difficult to prove, that the Gaussian blur quickly make lattices uniform, completely smoother them, and this is what allows us to take an arbitrary kind of worst case lattice and convert it into an LWE problem where there's no longer this discrete structure visible. Again, just some intuition. It's not. I cannot really give the proof. Let me remark on one other interesting aspect of this, namely the quantum part. Where does it come from? How come we need quantum in that proof? Something I haven't seen happen anywhere else. And here's where it comes from, right? So, as part of the proof, again, the proof aims to show that if you have an LWE solver, you can also find short vectors. As part of the proof, we need to perform a certain algorithmic task. I'll tell you in a minute what it is. But that algorithmic task, I only know how to do it quantumly, not classically. So previously, I told you there's nothing better known quantumly than classically. There is this task, but this task is highly specialized, not a natural task, where quantum computers do help, and this is crucial. So basically, this is a case where quantum computers are used not to attack a system, but actually to build a system. Sometimes the quantum computing idea is necessary for building the system, for proving security of the system. Even though I should say the fact, the question of whether quantum computers exist in the physical world is irrelevant here. This is a mathematical proof. So it does not depend on the existence of quantum computers. So why quantum? So how does it come about? And here is what happens. So it's somewhere along the proof, this is what you get. You get to a situation where you have a way, I call it an oracle, you have a way to solve the following task. And it should relate to the picture I showed you before. So you have a way to solve the following task, namely, given a point x, given a point y that's promised to be very close to a lattice point x, at some point during this proof, you have the ability to find x given y. So again, this is something that we believe is very hard to do. It would normally take me exponential time to solve such a task. So at some point during this proof, we managed to show that you're able to solve this task. If you give me a y that's somewhere in this small radius around a lattice point, I can find x back. Okay, so again, this seems like a fantastic birthday gift, right? It's something I don't know how to do myself. I would need tons of time to do this. Unfortunately, I don't see anything I could do with it. This seems like a totally useless gift because, well, as far as I can see, the only way to produce such y's is the following. I choose some lattice point x. I perturb it a bit. I add some small amount of noise, I get my y, and then I call the oracle with y, and the oracle tells me x. But I already knew that, okay? This sounds stupid, but the reason this happens is because the volume in space occupied by points that are close to lattice points is exponentially small. If you just choose random points, you'll never be that close to lattice point. So it seems that in order to generate a point that's close to the lattice, the only way to do it is to start from lattice point and add some noise. But then we already know the answer. So there's this paradox here. On one hand, we have this fantastic oracle that answers questions that we otherwise don't know how to answer, but we don't know what to do with it. And to the rescue comes quantum. Because this, even though it's so useless for classical computers, it's very useful for quantum computers. Because what it allows you to do is allows you to do this computation of going from y comma x, from this state y comma x to the state y comma 0 in a reversible way. So if you've seen anything about quantum computers, you know that quantum computation must always be reversible. If you do something, you have to go back. And at some point, we really want to convert y comma x into y comma 0. But normally, this is not reversible. Because if I only have y comma 0, I don't know how to go back to y comma x, because I lost the information about x. But given this oracle, allows me, given y alone, given y only, to recover x again. So it just made this transformation from yx to y0 reversible. This allows you to construct a certain state on the lattice and take the Fourier transform. And that Fourier transform allows you to recover some short vectors in the dual lattice. But that's beyond this sketch. So again, the idea is that there is at some point in the proof there's something we can do that we don't know how to make we don't know how to make use of it classically. Only quantum, and quantum it's because it allows us to do things reversible. So that's all I want to say about the proof. I want to show you. Let's switch gears a bit and show you a bit applications of this LWE idea. The first one is something we kind of saw before, the public key encryption. This just makes it a bit more precise. The private key, as I told you, is a number S. It should be modulo some n. Before I just told you choose a number 1001, but it should be modulo. It should be uniform modulo some large n. The public key is those equations, AIS minus BI equals roughly 0 with some small Gaussian even noise. And encryption, as we did before, we just take a bunch of those equations. So we have those approximate equations, linear equations on the secret S of the form AIS minus BI equals roughly 0. And then to encrypt, you can sum a bunch of those equations and either add 1 or not add 1. So I'm doing it quickly because I'll do it again in the next slide for a different application. To decrypt, you plug in S because I know S. I'm the one who chose S. I just plug S and check if AS minus B is even or odd. So that's one application. That's a standard public key encryption. But let me tell you about another application, which is far more exciting for me. Namely, this is fully homomorphic encryption. And this is something that dates back to the earliest days of cryptography, 1978, where Yves Edelman and Dertouzes conjectured that something like that should exist, or suggested this thing, but no one knew how to construct it until Craig Gentry, not far from here, IBM at Yorktown, showed how this can actually exist based on lattices, lattices and now LWE. What is this? What is this encryption? It's something quite remarkable. Sometimes people call it like encryption in the cloud. The idea is that you have some secret information, say your DNA, and you want to send it over to the company to do some analysis, like check how prone you are to certain diseases, but you don't really want to reveal your DNA to the company because, as you know, that DNA will later go to the other parties or be sold to advertisements for the government and so on. You just want the company to do that work, just tell you, how likely you are to develop certain diseases. And this is something that allows you to do it. You encrypt all your DNA using some secret key that only you know. You send the encrypted information to the company. They do the analysis. They don't know anything because it's all encrypted. They don't see what's in there. They send you back the answer, and you can finally tell if you're, what the answer is good or bad. This sounds totally counterintuitive. And actually, the way I describe it is impossible. Maybe you see why. Well, the company itself should not know the answer because that gives the company some information about my DNA. Turns out that the answer the company sends you back is also encrypted. So the company not only doesn't see the input, but also doesn't see the output. It just sends you some output back and doesn't even know what it sends. So this is a totally counterintuitive construction, but turns out these things exist based on LWE. So I'll just show you why such a thing can exist, just to give you an idea of how these things exist. So the idea would be this. I choose a secret S from modulo n, and I have this DNA. My DNA I want to encrypt, so it's x1 up to xm. I just use bits. And what I do, I just encrypt them as equations, as before. So for each bit, for each DNA, for each nucleic acid or half of it, I choose an equation, AIS minus BI, and it's either going to have even noise or odd noise. So this is going to be an either small random even number or small random odd number. So again, remember, AIS minus BI, when you plug in S, and only I know S, when you plug in S, you get either even or odd number. And that's going to be that secret, that DNA base pair. So now the server gets all this encrypted information. They want to perform an XOR operation. They want to add two numbers modulo 2. Well, that's easy. To add numbers modulo 2 is very easy. You just take AS minus B and A prime S minus B prime and just adds them together. Okay, when you add them together, you get, again, the server doesn't see S. It's an equation. S is unknown, but the server can still add those two and get A plus A prime times S minus B plus B prime. The server doesn't know what S is, but when you plug in S, what you get is the sum of those two things. So you get even number, if and only if both were even or both were odd. Otherwise, you get an odd number. Okay, so that's exactly what we wish to achieve. This is addition modulo 2 of the bit inside M. That's one way in which a server, without knowing anything about S or what's encoded in there, can do some operations on those encryptions. Okay? Multiplying requires more work, but since I'm running out of time, I'll just fast forward. But this is also something one can deal with. This was actually the main difficulty. That's why it took so many years to deal with multiplications. Okay, so there's the idea. You send extra encryptions of S squared to prevent some blow up from happening. But let me go to a completely different topic, something that we're working on in recent years, in the last 5 years, something I'm more excited by. We're trying to make this thing more practical. So one thing I didn't tell you is that LWE is efficient, but still not totally practical. So it would still require some maybe tens or hundreds of kilobytes to encrypt information, and people really want very, very efficient things. So we went to we started using lattices that show up in algebraic number theory, and those have been well investigated in the 19th century, partly as an attempt to solve Fermat's theorem, and Kummer is one of the people that improved many cases of Fermat's jet theorem using those ideas. So algebraic number theory is a well-developed theory. What we need is those lattices that they show up there. Those lattices have lots of symmetries, and they make them so much more efficient for us. Because of the symmetries, we don't have to store n vectors. We only have to store one vector, and the symmetries allow us to recover all the other vectors. So symmetry is a very good thing for us to make things much more efficient. So basically, in LWE, each equation has a scalar on the right-hand side, so only allows us to encode one bit or a few bits if you use even or odd. But in this, what we call ring LWE, based on algebraic number theory, you can now work with polynomials, and now each equation can encode many more bits. Again, just saying this seems like it should still be secure is a dangerous statement. We're now using lattices with lots of structure. But we have a theorem to back this statement, and the theorem shows something similar to what we saw before. If you can break this encryption, if you bring ring LWE, you get a quantum algorithm for certain lattices showing up in algebraic number theory. So I won't give many more details about this, but there's some statement that backs this statement. Again, the advantages are now the key sizes are only linear. It's much more efficient. And if you use the fast Fourier transform, everything becomes much faster. Again, there's much more I can say about that. But just for the last minute, let me just tell you about something exciting that happened in the last year. The thing is, the story is that around 2010, several authors, trying to be greedy and trying to get even more efficient systems, suggested using certain kinds of ideals. So if those of you know, ideals generated by short elements. So principal ideals generated by short elements in the field, in the ring. And these proposals were not really backed by security proofs. They said, oh, this sounds like it has to be secure. Right? We tried everything we know. And many people because there was no evidence to the contrary, so people took up on this and thought, okay, let's use this. This is very useful. We can do lots of nice things with it. It's very efficient, very fast. But a surprise result came about a year ago, where Campbell, Groves, and Shepard from the GCHQ, based actually on previous work by Alexei Kitaev and others, showed that there is a quantum attack on those schemes. So these schemes turn out to be insecure. And if you wish, you can read more about this. There's a nice story in a quantum magazine by Natalie Watchover explaining the whole story. Naturally, this was scary for us because now there's suddenly an attack we didn't know about before. But I think at the end of the day, the conclusion we have so far is those attacks are very specific to the mistake they did there. Because they wanted things that are unreasonably efficient, they had to go to those ideas generated by short elements. And those things turn out to be insecure. And it seems that the attack is very tailored to that. So we don't think the attack applies to anything else. So this is currently the state of affairs. So let me conclude saying that, yeah, you should all be using it. I hope next meeting, you all have it on your phone and so on. Lattice-based cryptography is practical nowadays, is versatile, is secure, and I really hope this will be the alternative in the future, in the post-quantum cryptography. Some of the things we're looking at these days, trying to improve the security proof, making it non-quantum, and most of the time actually we're spending on trying to understand exactly those algebraic number theory, trying to get more attacks there you really want to make sure this thing is secure. So this is where most of the effort goes now. But yeah, so I'm encouraging you all to look at this, maybe provide more ideas. But this is currently where things stand. Okay, thank you.